Welcome back to another explainer. Today, we're taking something incredibly complex and making it beautifully simple. We are going to completely demystify the abstract math behind the electrical grid. You know, the thing that powers our entire modern world. And we're going to do it by anchoring all those terrifying equations directly to physical reality. We are talking about the physics and math of alternating current, or AC. Let's kick this off with a bit of a provocative question. Direct current, or DC, is honestly pretty limited when it comes to large-scale power distribution. So why does the entire planet rely on a voltage that is constantly changing polarity? Like, why are we using a fluctuating wave instead of just a nice, steady, straight line of power?
Well, here is our roadmap for today to figure that out. First, generating alternating current. Second, the language of AC waves. Third, measuring AC, specifically peak and RMS. Fourth, visualizing those waves with phasors. And finally, putting AC into simple circuits. Let's get into it.
Section 1. Generating alternating current. Okay, picture a simple AC generator. What you've got is a rectangular loop of conducting wire, and it's placed right between the north and south poles of a permanent magnet. Now imagine this loop spinning counterclockwise. As it rotates, the sides of the wire actually physically slice through the invisible magnetic lines of force traveling between those two poles.
Let's break down that spin, step by step. As the loop rotates, the generated voltage, which we call electromotive force, or EMF, fluctuates entirely based on its physical position. In step 1, the wire is moving perfectly parallel to the magnetic field. Because it's not cutting across any lines of force, your induced EMF is exactly zero. But as it keeps spinning and hits a 90-degree angle for step 2, it is moving perfectly perpendicular to the field. It's slicing the maximum number of lines, giving you maximum positive voltage. Then, in step 3, it hits 180 degrees. It's parallel again, and the voltage drops right back to zero. If you keep spinning it, it cuts the field going the other way, creating a negative voltage. So that continuous physical rotation, it literally draws out a perfectly continuous sine wave.
Moving right along to Section 2, the language of AC waves.
When we graph that sine wave out, it is so cool because you can clearly see how the physical 360-degree rotation of our generator translates right into the math. The horizontal axis is showing your angle or time, and the vertical axis gives you the instantaneous value of the voltage or current. So one full mechanical revolution of our generator gives us exactly one complete set of positive and negative values on the graph.
And we actually call that complete set a cycle. Simple enough, right? The time it takes for the wave to finish just one of these cycles is called the time period.
Building right on top of that concept, frequency is really just a measure of how many of these complete cycles happen in a single second. So if your generator is spinning 60 times per second, you've got a frequency of 60 hertz.
And finally, the absolute highest point that the wave reaches, whether that's the positive peak way up top or the negative peak down at the bottom, is called the amplitude, or the maximum peak value.
Which brings us to Section 3, measuring AC, specifically looking at peak versus RMS.
Here's the problem. If the wave is constantly rising to a peak, crashing down to zero, and then going negative, how on earth do we actually measure its usable power? I mean, it's a moving target. Peak value tells us the absolute maximum limit it reaches, sure, but it doesn't tell us how much work it can actually get done over time. For that, we rely on the root mean square, or RMS value. This is the practical equivalent if we were using steady, unchanging direct current.
The absolute crucial point here is that RMS is just a highly practical translation for the real world. Think about it strictly in terms of heating. The RMS value is the exact amount of alternating current you'd need to generate the exact same amount of heat in a resistor as a steady direct current would over that same time. It totally levels the playing field. When you look at an ammeter or a voltmeter in your house, it's actually recording this RMS value, so you know exactly what your appliances are getting.
And we definitely don't just guess this number. We can calculate this mathematically, even for really messy, non-sinusoidal waves. We do this by dividing a current's half-cycle into small, equal time intervals. Then we take the mid-ordinates of those intervals, square them to represent their heating effect, average the whole thing out, and finally take the square root of that. Bam! It gives us a standardized, super reliable measurement of effective power.
All right, Section 4, visualizing waves with phasors.
I want you to imagine a line rotating around a central point, like the hand of a clock, spinning at a specific angular velocity that perfectly matches the frequency of our generator. Now, if you were to shine a flashlight on that rotating line and track its shadow projecting onto the vertical y-axis, that projection perfectly draws out our alternating current wave over time. The length of the line is the amplitude, and its angle gives us the instantaneous value.
Now, why do we use these phasors? Honestly, because they take absolutely nightmarish complex math and make it incredibly simple. If you have two different currents with the same frequency, they might not hit their peak at the exact same time, right? They have what we call a phase difference. But because these phasors rotate at the exact same angular velocity, that phase difference stays perfectly constant. We can lock it right in place and evaluate it.
What this means is that instead of doing agonizing calculus to add up multiple fluctuating sine waves, we can treat them just like we would physical forces. We can combine these phasors using simple geometry, like the parallelogram method, or just break them down into vertical and horizontal components and add them up algebraically. It literally transforms moving waves into static, easily solvable geometry. It is a total game changer.
And lastly, Section 5, AC and simple circuits.
Let's look at how this plays out in real life with two basic setups. In one setup, we have an alternating current flowing through a pure resistor. In the other setup, that exact same alternating current flows through a pure, coiled inductor. And they react to the wave in completely different ways.
What happens here is absolutely fascinating. In the purely resistive circuit, the applied voltage simply has to overcome the ohmic drop. Because of this, the current and the voltage stay perfectly in phase with each other. They peak and cross zero at the exact same time. But in the inductor, the changing current actually induces a magnetic back EMF that literally fights the change in current. This opposition physically drags the current, causing it to lag a full 90 degrees behind the voltage. The voltage is pushing hard, but the current is delayed. And understanding this lag? That is exactly how we design the motors that power your electric vehicles and household appliances. Now, in the real world, circuits usually have both. When you combine standard resistance with this inductive delay, which we call inductive reactance, in a single series circuit, you create a total unified opposition to the AC wave. We call this combined opposition impedance, represented by the letter Z. It's found by taking the square root of the resistance squared plus the reactance squared. It's the perfect way to calculate exactly how much a real-world circuit pushes back.
So we've seen how a spinning magnet creates a wave, how we measure its true power, and how electrons are fundamentally pushed and delayed through basic parts like resistors and inductors. All of this leaves us with a wild thought to explore next time. How do we calculate the exact point where these delays perfectly cancel each other out, creating resonant frequencies that allow us to tune our radios, filter signals, and power the entirety of global communications? It's like a giant puzzle. Until next time, keep exploring the physical realities hiding behind the math.